Good afternoon, everybody. My name is Fred Nauer. I'm the Chief Flight Instructor for Thunderbird Aviation. I'll be giving you a safety seminar this afternoon about summer weather hazards. And we're recording now, so I have everybody on mute so we can make sure that keep the noise down to a minimum. I was trying to work with this with my phone a little bit earlier, and I got a huge amount of feedback, so that's why I've muted everybody to make sure that we avoid the feedback loop that normally happens on these kind of calls. So I'll try to keep my eyes on the participant level here just to make sure nobody else signs in, but we'll just get started with the process right now. So I'm going to move over to the other part of my iPad here and get to the briefing. So today we're going to talk about the weather, how to find it, what it's going to look like when we're looking at METAR and TAF abbreviations. We'll look at sources of weather information, concentrating on the Aviation Weather Center and the Flight app. You can get the same thing if you're a Garmin person. The same information will come up. You just might have to do a slightly different way to do it. And we'll conclude today by talking about the severe weather that can happen in the summertime, both flying wise, thunderstorms and microbursts. And then we'll finish up with a talk about heat and how it affects your body as you're trying to fly the airplane. So first, some weather abbreviations that you might see on the METARs and TAFs throughout the summer. So the RA is nice because that's still in English. That's the same as it's always been for those of you who have been looking at this weather information for years and years. So the RA is rain, and as with any of these, if it's just the letters itself, it's moderate. If there's a plus, that means it's heavy. If there's a minus, it means it's light. DZ, another English word. That means drizzle. FG, usually something that might happen in the morning or late in the evening. For fog. You just have to be careful when you're about to go flying, especially from the daytime into the evening, to make sure that the temperatures and dew points are not too close together, because if the temperature and dew point is close together, there's a possibility of either clouds forming, or if it's really humid, the fog might form on the ground, and then you might have a little bit of a hard time trying to get back to your airport, whether you're instrument or VFR. BR, the first one that, because we switched over to the ICAO system a few years back, this is the first one that's not in English. So everybody here in America calls this baby rain because it's officially for mist, which is, the BR comes from the French word. I don't know how to pronounce that, but that's the French word down there on the bottom of the slide there. That is the French word for mist. And the difference between fog and mist is basically just how what the visibility is. Fog is usually the visibility is down below a quarter mile. Mist is something above a quarter mile of visibility. Then the big thing that can happen in the summertime, TS for thunderstorms, and we'll talk more about how they form and how to avoid them a little bit later. If you're looking at the METAR on the Aviation Weather Center, sometimes in the remarks section, you'll see something that looks like this, TSNO. And so anything that has an abbreviation for a weather type and then the letter NO means that portion of the ASOS or AWOS is not operating. So in this case, TSNO is lightning detector not operating because there's not a thunderstorm unless there's lightning going on. Then in the cloud section of the METAR or the TAF, TCU is towering cumulus. Those are the clouds that are building up that may eventually become thunderstorms. And once they become thunderstorms, they'll be TS, but in between there, if there's no lightning coming out of it, then it'll be a CB type of cloud, which stands for cumulonimbus. Cumulo meaning that they're all being built up like towering cumulus, but the nimbus part means that there's actually rain coming out of those clouds. Then if you're looking in the remarks section, this one here is pressure falling rapidly. So if you see this on a METAR, it probably means that there's some sort of storm moving in and the barometric pressure around that airport is falling fairly quickly. So there's a good possibility that severe weather is connected with that rapid pressure drop. And finally, way back in the old days before there was METARs and TAFs, the abbreviation for a tornado at the airport was just the word tornado. Now they make it an FC. FC means funnel cloud. And if there's a plus with the FC, that means it's a tornado that's hit the ground, or a water spout that is, is over in the water. So stand by just a second while I drop off here, while I go back to this thing here, so I can let somebody else in, and then we'll continue. So, sources of weather hazard information. Aviation Weather Service, Flight, 1-800-weatherbrief.com is a website that belongs to the Leidos Corporation, which now runs all the flight service stations and gets you the official weather briefing. And by getting the weather off of 1-800-weatherbrief.com, if you put in your name and the tail number and where you're flying, it'll actually be an official weather briefing also. You can do SkyVector. That's another online source that not only helps you with flight planning, but also can give you all sorts of weather information. And like I talked about before, we got the Garmin system, which will be sort of like the Flight, maybe just in different colors. And AOPA also has a system in there for flight planning that you can use. It'll also help you with the weather information and being able to determine where weather hazards may be. So let me leave the PowerPoint here for just a second and go to the internet portion of my iPad. So the Aviation Weather Center, AWC, you can just type in AWC into your search engine, and this will come up, and it has all sorts of great information. What I have here first is the AirMets and SIGMET section, and it's concentrating on the SIGMET portion. And as you can see, it's marked with a TS. I go the grid across the bottom here with all those squares tell you what it all means. So TS means there's actually thunderstorms happening. CONV is convective SIGMET. Tropical problems, turbulence, icing areas, and VA. Now we have to go kind of far afield here to get the VA portion. And that's probably not a summer weather hazard here in the United States unless Mount St. Helens decides to let go again. But the VA is volcanic ash. So here we must have a volcano just somewhere south of Japan that has decided to let go, and then the volcanic ash is being blown by the prevailing winds there throughout the area. It became something that is important, not so much for us here in the United States, but for jets flying around the world, because the volcanic ash is not visible by any onboard radar that the airlines have. You can fly into a volcanic ash cloud and not even know it happened. And then you got all sorts of problems like scoring of the windscreen. If the stuff gets inside your jet engine, the jet engine will quit working. Ends up being a bad day all around. So that's the convective SIGMETs and thunderstorm area information that you can have. There's also an AirMet section that you can do. So this is the basic graphical AirMet. So this let you not have to go in there and try to figure out where all the points are when in the wording version of the AirMets to figure out exactly what the size of the AirMet is. It takes all that stuff and draws it right on the map for you, so it makes it real easy to see. And now this is for all levels, so that's why you're seeing everything. But so including this icing level, which goes all the way up to 43,000 feet. Probably not something we'd be worried about. But on this one, you're not going to get the thunderstorms. You're just going to get the areas of turbulence, low level wind shear, icing, freezing levels, IFR, and mountain obscuration out here in the out east. Problem with having all of them on here, sometimes it's hard to get exact, just the stuff that's underneath there. There's also a graphical version of this where you can select it individually to see exactly what you're looking for. If you're not a high person, you can just look for turbulence low. And for the mountain obscuration one, then you just pull that up and get it individually there. The nice thing about the turbulence, though, is that it does give you the levels that it's at. Out here in the mountains, surface up to 16,000 feet. Down here in North Dakota, Nebraska, and southeast western Minnesota, we got it from the surface up to 8,000 feet. There's also various ways of looking at turbulence. You're looking at the segments a little bit earlier, but now they have some experimental stuff in the Aviation Weather Center, including this turbulence guidance here. So first thing you have to do is up in the corner here, select the type of aircraft you are flying, and then it'll let you know. It'll still give you all the different types of turbulence, but it'll grade the coloring based on the type of airplane that you're flying. So because turbulence affects different aircraft different ways. So then the other thing you can do is decrease the altitude to figure out where the turbulence is for the altitude that you're actually going to be flying. You notice as I go up in altitude here from 1,000 up to 3,000, there's nothing here in the western part of the state, but that's because we're still underneath the ground yet. So you got to get up above 5,000, 7,000 feet before you actually start getting the stuff over the mountains. But the color coding on the bottom here tells you exactly what level of turbulence you can expect based on the altitude that you've chosen. Wait a minute. Look at all that. And the convection stuff we've already looked at. So let's go to Flight. So there's in the upper left-hand corner of Flight, there's a system that you can use to draw the stuff on the map like we just looked at. But you can, if you like to look at the same sort of stuff that's on the Aviation Weather Center site, there's this imagery section on the bottom. As long as you're hooked up to a Wi-Fi someplace, you'll be able to pick this stuff up. And you can choose whatever system you're looking at: convective outlooks, convective forecasts, prog charts for the types and intensity of the rain that's going on, the different cloud surfaces, winds aloft, icing levels, if you're interested in that stuff, turbulence at various altitudes, just like we talked about before, the same color coding we were looking at on the Aviation Weather Center. But if you're on the map and looking at specifically for your type of the area where you're flying, in the upper left-hand corner, there's all sorts of weather choices on the right side of this thing that you pull up here. On the ground, you can do both radar composite, which gives you all the radar from at all levels, including the lightning strikes that are happening out there. So you can tell which ones are exactly whether they're thunderstorms or not. And while you're on the ground and hooked up to Wi-Fi, you can also get the lowest tilt so that for those of us that are flying down here in Indian country, like they call it, we can get to where the intensity of the precipitation at the lowest part of where the precipitation is falling from. Then there's satellite stuff that's kind of hard to see, but you got the icing information. Kind of too warm today, not a whole lot of icing, but I'll give you the different color codings down here. Turbulence. Again, the color coding of the various turbulence. And again, over here, you got a little level thing that you can move to change the level. Let me get rid of that. VFR section will make it a little bit easier to read. So you can see the different colors changes as you change the altitude over on the side. Surface analysis gives you the information just like the chart that we were looking at in the image section, where the highs and lows and fronts are. The graphical image of the winds at whatever altitude you choose here. So this is up high. Seems like we got a little backwards flow today. And the lower you go, the more the wind shifts around. So you can go down to an altitude where you normally fly at. You can almost guess where the lows are because of the way the wind is wrapping around the low at the low level there. So the different color coding now will help you figure out what the speeds of these winds are that we were just looking at before. The hazard advisor is more for when you're flying, so that one doesn't work right now. But you can do, get rid of the winds here, airmet, SIGMETs, and weather advisory. Again, you can select down here exactly which ones you're looking for. So in the summertime, where it's thunderstorms in areas like that, the yellow ones are SIGMETs, the red ones are where the thunderstorms are actually happening. And if you overlay that with the radar, you notice that the places where the lightning are from the radar is exactly the places where the red information is on the map itself. Now so the thing about the radar, let me move in here. The information that you're going to get in Flight, and Garmin is the exact same way, although in just about any non-radar information you're going to get in the airplane. If you have a radar attached to your airplane, then that's instantaneous. That's the information where the precipitation is right at that second. But if you're pulling stuff up on Garmin or Flight like this, or any of the weather systems that you have on board your airplane, to get a radar depiction on there, it's always going to be probably at best 15 minutes old, and probably at worst 20 to 40 minutes old. So you can use this for general weather information, not how do I fly between these storms to try to get around all this stuff. Because where it's depicted on the screen here is not where it is right now. Yes, it looks like it's real, and it looks like it's right now. You can even, on the ground, push a little button and watch the storm move across and watch it move so you can get an idea which way it's going. And even though it says this last one, it was 0 minutes ago, this last image was 0 minutes ago, but by the time the image gets to here and it's sent out by Flight 0 minutes ago, it's probably 15 minutes old. So especially during thunderstorms and stuff like that, they usually grow so fast and at certain times can move so quickly, you don't want to use this as a navigation tool, except for here comes a thunderstorm, let me get on the ground and wait till it passes. You don't want to use this for a navigation tool saying, oh, it looks kind of like light green up here in this part of just in the northern part of this red area here, so let me fly through there. That's not going to work, because by the time you get there, that thunderstorm that's over on the side is going to be right over the top of you. So don't use this for navigation, just use the radar stuff for information. Then and you can use, so figuring out where the ceiling of visibility, that'll also help you figure out if there's any storm, maybe not so much storms, but how the storm is affecting the ceiling and the ceiling that you're flying through, or the visibility that's available underneath those clouds, or the flight category of the airports, which is, color coded as green is VFR, blue is marginal VFR, red is IFR, and pink is low IFR. So you can use that to get a general idea about what that severe weather may be doing to the ceiling of visibility around your route of flight. So, two types of thunderstorms that we have to worry about. One of them is single cell. Well, this one, this is one that they basically teach you about when you're in all the books when you talk about the various types of thunderstorms. I found a little video here that I can pull up, and I tested this earlier, so all the voices and everything that happened in this should come through.
In this video, I'm going to summarize the life cycle of a single-cell thunderstorm. Basically, single-cell thunderstorms have three stages: the cumulus stage, the mature stage, and the dissipating stage. In the cumulus stage, the cloud is dominated by updrafts, as a cumulus congestus or towering cumulus cloud develops. As updrafts accelerate, low-level air converges in from miles around to feed the updraft. Eventually, as the cloud grows very tall and cold, the top of the cloud becomes glaciated and a cumulus...
So the updrafts will pull air in and down at the air levels we fly. It may cause severe changes in wind direction and that type of thing as the updrafts start to continue. Once the downdraft, so this is the cumulus stage, now he's talking about the mature stage where it starts to rain. So that now they're saying that the thunderstorm kind of lays over its side so that it will continue to go through this loop for a while until this cloud moves, and so then the updraft part moves over the part where the ground is now cool, and will basically shut the storm off. But the thing you want to worry about as far as aviation is concerned is this leaning over thing that happens, because inside this cloud is rain going up, rain going down, and at the higher altitudes, you even have hail and icing going on. So especially the hail can get spit out the top of the cloud and drop way away from where the thunderstorm is. So usually when you're flying around, you want to make sure that you're at least 20 nautical miles away from the thunderstorm on all sides. On the windward side, you want to stay away from that because of the hail that's coming out and being blown that direction. On the upwind side, you want to stay more than 20 miles away, especially low level, because that's where the air is coming to feed the thunderstorm in the first place, and there'll be quite a lot of turbulence near the ground. Let me turn this one back on.
Nimbus cloud is born. The glaciated top of the cumulonimbus cloud is a sign that the storm is about to reach the mature stage, which formally begins when precipitation reaches the ground. In the mature stage, the storm cloud contains both prominent updrafts and downdrafts. When the downdraft splashes down on the ground, it spreads out laterally, much like water from a kitchen faucet hitting the sink below. The gathering area of rain-cooled air spreading out along the ground is called the cold pool, and its leading edge is called a gust front or outflow boundary. If you've ever felt a rush of cooler air and gusty winds before a shower or thunderstorm, you've noticed the passage of the gust front.
And so that's why you don't want to take off if there's a thunderstorm in your area, even though the thunderstorm looks like it's far away. I talked about the updraft stuff already. So now when the downdrafts happen and you get this gust front out the leading edge of this thing, that could really severely change the wind direction and intensity of the wind at your airport. So anytime there's a thunderstorm anywhere in the area of your airport, it's best to just stay on the ground. So my finger's not letting the play button happen.
The mature stage is really the most intense part of the storm. Updrafts attain their fastest speeds, lightning is most frequent, rain is heaviest, radar reflectivity is greatest, cloud tops are highest, and the glaciated anvil that forms near the tropopause becomes most prominent. But after about 10 minutes or so in the mature stage, the cell transitions to the dissipating stage as the storm's cold pool expands and cuts off the updraft's access to buoyant, warm, moist air. As the updraft fades, the cloud becomes dominated by downdrafts in the dissipating stage as the storm rains itself out and dies. The birth, life, and death of a single-cell thunderstorm typically takes less than 45 minutes. As a final summary, here's a two-part schematic showing the evolution of a single-cell thunderstorm. The top panel shows a time sequence of a cross-section through a single-cell thunderstorm, showing idealized radar composite reflectivities. The bottom panel shows a corresponding time sequence of idealized radar base reflectivities, with the observer looking down on top of the single cell.
So this is why when you're using any of the weather information in the air, and you're flying in the airplane, you don't want to use it to figure out how to get around a thunderstorm, because by the time you receive this 15-minute image, the thunderstorm is probably over here in the 25-minute zone. And so the precipitation, the intensity of the storm can be much, much greater than what is depicted on the screen itself for the on the screen itself for the radar coverage, the radar information that you're getting in the airplane at that time.
The first 15 minutes or so are spent in the cumulus stage as a towering cumulus cloud develops and precipitation-sized targets develop within the cloud toward the end of the cumulus stage, which generates some radar reflectivity within the cloud. By 20 minutes or so, we're into the mature stage and rain reaches the ground, while the downdraft splashes down and the gust front spreads out from the storm. You can sometimes see gust fronts on radar images because the radar detects things like bugs and small airborne particles like dust and dirt, which collect along the boundary because of low-level convergence. After about 25 minutes, the storm begins to transition to the dissipating stage as the gust front spreads farther out from the center of the storm and the updraft fades. Now dominated by downdrafts, the storm is essentially in the process of raining itself out and dying.
So the single cell type of thunderstorm is a rarity. They're very seldom do they, or they happen and they're severe, but the one that is even worse, the worst kind of thunderstorm is the squall line, because like in the single cell storm like we talked about, eventually it gets to the point where it's raining over its source of heat from the ground and basically shuts off the source of heat, and the storm goes into dissipation. The tricky part about the squall line is A, it's a whole line of thunderstorms, so it's really hard to navigate around, and B, it's moving. So it will always be moving over areas that are continually warm and hot and feeding the storm as it continues to move along. So the intensity of the storm in the squall line gets to be much, much greater. So let's take a look at this one here.
A squall line is, simply put, a line of storms. Squall lines can also be called multi-cell linear storms, but the most common term used to identify these storms is squall line. A squall line consists of storms situated along a gust front at the leading edge of the line. The gust front acts as the system's updraft as air is lifted upwards along the leading edge of the line, even as colder air rushes out.
This is exactly what happens in a squall line. It's usually created by a fast-moving gust front. I'm sorry that the pause thing covers up the screen here, but as you can see the arrow there, this is where the cold front is, and the warm air is being ridden up over the top of the cold front, and that causes the lifting action that was needed for the thunderstorm to be created in the first place. And then as the front continues to move, it keeps moving this thunderstorm area over warmer ground, and it continues to feed the storms as they move along. So it's very hard so these are the kind of storms that can last for hours on end as they move across usually a big hunk of the country.
And away from the storm's course. Lines of storms can persist for hours and even days as they move east or south. A line of storms will see its biggest severe weather threats along and just behind the gust front. The main severe weather threat from squall lines is damaging winds, but large hail and even weak tornadoes are possible. Another threat is significant flash flooding, especially in situations where the line itself is moving slowly as individual cells move over the same areas repeatedly. Linear systems are easy to track and predict, as they typically follow a pretty straight path. Lines of storms can be incredibly damaging, and thus you should always pay special attention when one is approaching your area.
So back to Flight here. Let's go back to our composite radar here. So as we can see, so only do one at a time. So as you can see, so back it up here, Fred, come on. So on the surface analysis chart,
coming up.
Surface analysis chart, you can see where the front is across the country. Stationary fronts can create the same sort of situation, although most of the time it'll be a front that is moving, because as we look at the surface analysis chart, then go back to the radar, we notice that there's a lot of thunderstorms right along that same area, especially the spot where it's not stationary, but actually is the cold front that's actually moving through. And so that's why these things are so dangerous, because as they move across the country, they'll continue to gain the hot, warm, moist air that it needed to fuel the thunderstorm in the first place, and just get more and more intense as it goes across, as it continues to travel across the ground. So in this situation, something that's from a flying situation, the best thing to do is, looking at the squall line coming at you, obviously don't fly at that point, wait till it gets past you, and then just be flying the other direction. If you see this coming, if you see this on your onboard information that you're flying along with, the best thing to do is to find an airport to land on the leading edge of this thing, at least 20 miles away, so you can be safe during your landing, and then make sure that then just wait out the storm, because it should, depending on how fast it's moving, should be able to get by you in sometime in the near future. Then the other part that is very dangerous is because created by a thunderstorm is called a microburst. As this became very, very evident in the late 1990s, when there were actually airliners that crashed because they flew through a microburst. And so then it became a very urgent situation to try to figure out what kind of systems they can create, and to be able to figure out exactly where the microbursts are. So basically, that's why they, in Minneapolis, they moved the weather radar from the airport itself down to Chanhassen, because they needed to be able to see all the wind directions and wind velocities created by the Doppler radar from away from the airport, so they can detect these microbursts. Let's go through this video real quick here, so I can give you an idea of what we're talking about. So this is one of those, it's all music. So you can see, coming out of this thunderstorm, a very strong indication of the rain coming out of that storm. And then when it hits the ground, it starts to spread out as that strong downdraft pulls a lot of moisture down with it, and then the moisture and the downdraft hit the ground. So that's what this cloud thing is showing you. As the cold, wet air hits the ground, it spreads out, and the area across the ground is the place where most of the danger happens in the microburst itself. This is not a microburst, this is just severe turbulence. So that's why I put this picture up of the microburst on the slide here. As the microburst comes down and it hits the ground, the air flows out and does this little loop on all sides. It's just depicted in a 2D picture, but all 360 degrees around this microburst is all doing this. The part that was causing problems with the jet airliners is if the airport is on the inside this loop here, when they get to this section, the wind is a tailwind and becomes a performance enhancing situation. If they're trying to fly a glide slope, the airplane is going to climb above the glide slope. So then the pilots of the airplane pull the throttle back and lower the nose to try to stay on glide slope. And then the airspeed starts to then it moves from the tailwind to this downdraft. And now the power is back. The airspeed is low, and they don't have enough oomph on the engines to be able to overcome the downdraft, and the airplane just basically pancakes right into the ground. So, when I was flying for the airlines, and they gave us our microburst training. Basically, if you had a large change in airspeed near an airport where their thunderstorm was going on, the only thing you could do was don't try to stay on the glide slope. Just go around. Max power, start to climb, and hopefully then you'll have enough climb rate to avoid the downdraft, to not be pancaked by the downdraft once you hit it. But that's why the airports have spent millions of dollars. When it first started, last century, it was just little wind vanes all spread out all around the airport to detect which way the wind is blowing and what the direction was. And if there was a big difference between wind direction and wind speed on one part of the airport than the other, then it was obviously there was something happening. Either a thunderstorm was approaching or maybe a microburst was happening, and they could warn the pilots of those things going on. Now with Doppler radar, they can see, like they talked about the bugs and stuff on that other slide where they're talking about the weather depiction of the thunderstorm. They can look at the speed of the bugs as they're being blown around by the wind and tell where there's a change in velocity, and then fairly accurately determine exactly where the microburst is, and figure out when it's exactly time to shut down the airport where the microburst is going to be most dangerous to the airport itself. For us in our light little airplanes, for most of us are on this seminar here, then again, if there's any thunderstorm activity in the area, the best thing to do is just avoid it. Don't even take off. Fly away from it if you're in the air. Get on the ground before it gets there. If you're on the ground, stay on the ground, because in my the Piper Warriors that I fly here at Thunderbird Aviation at a crystal operation, there's no way in heck we're going to be able to fight a microburst. So there's no, it's not even something worth trying. It's just basically in a severe weather in the summertime for thunderstorms, squall lines, and eventually and occasionally microbursts coming out of those thunderstorms. It's just better to just be able to stay on the ground. Oops, wrong direction. So the other thing that's been happening, I just heard on the news this morning, June was the hottest month on record. That seems to be happening a whole lot lately. And, for whatever the reason is, but yeah, so there was lots and lots of days in June where it was really, really hard to, really, really hot. And if you were out there, like a lot of my instructors were out there trying to fly around and do lessons all day long, we had to make sure that we kept a close eye on things to make sure that their bodies weren't being too affected by what was going on in the heat. The main problem with extreme heat is dehydration. So the only way to alleviate dehydration is to take water with you. But then, like for me anyway, that means you got to flight plan things a little bit differently, because if I'm drinking water while I'm flying, that means my the places that I need to land at needs to be a lot shorter than if I didn't drink any water before I went up in the air, because for some reason all of a sudden I've developed this very, very small bladder, and I got like an hour's worth of flight time in me, and that's about it. So I got to make sure when I'm doing lessons and stuff that there's always an airport nearby that I can go by, and especially in the summertime, you want to make sure that you continue to drink water to avoid the dehydration. The next extreme portion or the next thing that happens to your body during extreme heat is heat exhaustion. That's where you feel very, very hot. Your temperature has probably climbed above 100 degrees. Your body temperature has climbed above 100 degrees. But at this point in heat exhaustion, you're still sweating a whole lot. There's still a lot of moisture coming out of your body. And so that's the first indication that it's time to stop whatever you're doing and get inside, get to an air-conditioned room, and just sit down and rest for a while. Because if you let the heat exhaustion go too far, then the next thing that develops is heat stroke. You know you're in heat stroke when you feel really, really hot. Now your temperature's getting above 102, 103 degrees, and you're not sweating anymore. If you're like that, you need to call 911, because that's an extreme situation, and just sitting in a cold room is not going to help that. You need medical attention if you get to the heat stroke level. So like the slide says here, make sure you're drinking lots of water, even if you're not thirsty. Avoid caffeine and alcohol, because both those things dehydrate you. And obviously, as pilots here, avoiding alcohol is also a regulatory requirement. Don't eat a big, huge meal. Make sure you eat lighter, smaller meals throughout the day, and wear lightweight, light-colored clothing to help reflect and make it easier to sweat. And the light-colored clothing will reflect some of the sunlight off your body as you're walking around. So on the aircraft side of things, in the last Thunderbird Aviation safety seminar from our director of maintenance, Paul Block, in his talk there, he talked about what happens to airplanes in extreme heat. So I put the YouTube address down there, and I'll click that in a second too, so we can take a look at our YouTube page, our YouTube channel. But as a quick reference, flying an airplane during extreme heat means you have to keep track of very close eye on the temperatures of the airplane. And for most of us in our air-cooled engines, the only way we can do that is to make sure we keep an eye on the oil temperature. Then most likely will be a problem right after takeoff, because the airplane's been on the ground, taxiing around in the extreme heat with not a whole lot of air blowing across the engine. So the engine itself is going to be hot, plus added to that, the heat outside the airplane. And so keep a close eye on the oil temperature. It'll usually peak out or even go into the red on the high side just after takeoff. So if you're flying around in extreme heat while you're trying to climb up to the altitudes where the temperature will drop and hopefully get down so that things cool off, including the cockpit inside the airplane, then keep a close eye on the oil temperature. If you're climbing and the oil temperature is starting to get up towards the red line on the high side, you need to pull the power back and continue your climb, but climb at a lower rate so that you can lower the nose and get more airflow through the front of the engine to help try to cool off the engine itself. But there was one of those days in June that I was flying with a student, and I decided, let's see if we can get up there to help cool this thing off. And we went up to 7,000 feet, and the temperature outside was still 90 degrees. So sometimes there's nothing you can do about it. The temperature is just going to be too hot. And on those days, it may be better just from an aircraft and human standpoint, it may be better just to be able to stay on the ground. But the trick with our Thunderbird channel is if you go to YouTube and ask for Thunderbird Aviation, 90% of the videos that show up are the ones for the Thunderbirds from the Air Force. So you got to go to https://www.youtube.com/user/Thunderbird Aviation, and that will only be our videos that are on channel. So we tap that and we go to it. So the time between overhauls and hot weather operation that you can see on the bottom of the screen here, that's the full talk. We talked about it. He talked about an hour, and that's the full talk there, and he'll go into a lot more depth than I did about the hot weather operations and how they affect your airplane. But all the other seminars that we've been doing are also on the channel. My flight one, some of my earlier ones about winter operations and things like that, they'll all be in here. So you can go to the Thunderbird Aviation channel on YouTube. This talk today will be archived on this site probably within the next week or so. Another way to be able to get to this site is go to thunderbirdaviation.com, our website. Go down to the flight training section, and somewhere in there it'll talk about seminars. You click on that and it gives you a link to our YouTube channel here. Speaking of maintenance seminars, next weekend on Saturday at 1 o'clock, Paul Block is going to talk about continuous talk on preventive maintenance for aircraft. This time he's going to be talking about aircraft struts. For those of you, for you Piper people out there, it'll be how to adjust and service all 3 struts. For you Cessna people, you'll be able to learn all about that and how to handle the stuff that you need to know for the nose gear strut. So that's next Saturday, July 17th at 1 p.m. in the afternoon. You go to, for most of you who signed up on the FAAsafety.gov website, you can go to the exact same spot, find this stuff, find this seminar, and sign up for it to be included in the invitation for next week. So, I think I talked too fast. But, so, let me, and my next seminar is going to be the second Saturday in August, and I'll talk about weight and balance, both how to determine it using various systems, including a pencil and paper, and some of the terms that are included in weight and balance that people kind of sort of know in their minds, but kind of forget. And we'll also be talking about, and like I say, giving examples of weight and balance and what the effects of an out of balance airplane are on the characteristics of the aircraft itself as you go flying around. So we'll talk about weight and balance next month on the second Saturday. So let me go back to my Zoom section here. Are there any questions? I think I muted everybody, but you can just tap the microphone there and turn your microphone back on, and you can ask me a question.
Fred, I put one in the chat box about haze.
Stand by. There we go. I'm fish. For some reason on my iPad right now, I don't have the chat box. What was the question?
Basically this, for me, the biggest nemesis for flying in the summer months, VFR primarily, is haze. I have a hard time predicting when haze will be encountered, because the METARs and the TAFs, haze is at the ground level, but when you're flying along and it's hazy, it just takes the joy out of it, because first of all, you're nervous about other traffic, and trying to identify ground checkpoints in haze is almost impossible unless you're right over them looking straight down. So just as a practical matter, how do you deal with haze in the summer months?
Yeah, you're exactly right. There's age. I just wrote that down. I need to add that to my little thing at the beginning of the process here. Because haze, like you said, sometimes haze is down near the ground. Sometimes it's a level. You can see all sorts of stuff if you're down below a certain altitude, but you get above a certain altitude, and now you're above the haze layer, right, and the sun is shining down on the top of the haze layer, and the whole Earth disappears. It's not cloudy. Every METAR and weather system that you look at says it's clear in a million. But yeah, so so haze is normally going to happen in areas where there's a high pressure system over the area, and it's going to be holding the air down. So the haze happens where the normal rising of air, I back up. So it's an area where there's a inverse in temperature, where there's hot air above and cooler air underneath. So the air rises to a certain spot and stops because of the haze, because of that temperature inversion, and that's usually where the haze layer forms.
Right.
The haze is not a predictable kind of thing because it's not really a phenomenon like fog. You can't look at temperature and dew point or look at, you know, and determine whether there's going to be haze or not, because sometimes it's just, the haze is just smoke particles in the air. It's not a moisture derived thing at all. When I was learning how to fly in North Carolina and doing my initial flight instruction out of Kinston Airport in North Carolina, in the summertime, if you didn't send a student out with 3 miles visibility, they would never fly because the salt particles would come in get blown in off the coast from the ocean, and that salt particles in the air, along with all the pollution and smoke, would make the visibility in some places 3 miles at best.
Mm-hmm.
So again, yeah, there's really no way to predict it. The trick, you know, so it's one of those things where you basically have to do your own kind of PIREP, you know, send out a weather ship and see if where the haze layer is, can you stay below it and still be safe to be able to see things, or is it high enough up that you're going to be able to get to it but not, you know, and be able to stay under it and be able to fly high enough and still be able to do your cross country stuff, or, you know, what layer is it at, what level is it at, so you can avoid getting above it so you can't see the ground in the first place. Did that help?
Yep, it sure did. The one thing that I've done is kind of wait for like a cold frontal passage, because after the cold front goes through and all the bad weather has gone through, it seems like then the flight visibility, ground visibility are usually really good. But then if you wait too long and you wait into the period of quote good weather, then all of a sudden, you know, too much of a good thing, then suddenly that air becomes stagnant and the haze starts forming.
Yeah, exactly.
Okay. But
yeah, because the cold front moving through, especially in the beginning part, that's where the temperature inversion happens.
Right.
Because the cold weather is low and the hot weather is high, and so that's where the temperature inversion happens, and that's the perfect place for haze to form. Exactly.
Right. Right. So just the quick question is, do you know of any sort of predictor of haze? You know, thunderstorm probability and all that stuff, but anything for haze itself?
Not that I could think of. Let me write that down so I can add this next time I do this one next year. I will make sure I add that to the system to see if there is anything out there that does it, because all the stuff that you can see, you know, I pulled up all the stuff that you can see in the Aviation Weather Center, and you notice that haze wasn't one of the choices. So right. I think it's one of those things that the weather people just kind of throw up their hands at and say, yeah, it happens, but you know, there's nothing that they definitively can use to say, and this is where it's going to be.
Right.
Unfortunately.
Yeah. For low time VFR pilots, haze, at least for me, it was really unnerving. You know, thunderstorm, you can kind of see it, you can predict it, you can see it on the charts, whatever, but haze, yep. All of a sudden you don't know that you're in it until you're in it.
Yeah, exactly.
Yeah. Okay. Thank you.
No problem. Any other questions? No, now that I stopped sharing, I found my chat thing. Okay. So thank you all for attending today. Like I said, I've been recording this whole thing, so I'll have my YouTube guru put this on the YouTube channel sometime next week. So tell your friends about it. They can go in and watch it there. If there are no other questions, we'll end today's session.